cascode transistors like this, the R out has a terminate that is the GM of the not the input transistor, but whatever comes above the input transistor. So if you can increase the GM of this thing above the input transistor, then you've just increased your R out, not your GM. Okay. This GM shows up in the R out equation. You're actually increasing R out when you're increasing the GM of this device right here. Okay, so that's gain boosting. And I'm just, let's see, pointer power. Okay. So a couple of things to know about gain boosting is that you're building this, except you're going to have an amplifier here, an amplifier here, an amplifier here, and an amplifier here. You have to gain boost both top and bottom. If you have a much bigger RO looking down than you do looking up, then the stuff on the top is going to dominate. It's not going to matter if you made this RO bigger, because all the current's going to go through the smaller R out. It's the same thing when you have a passive load on a diff pair or on a common emitter. That RO looking down is really big, but it doesn't matter because all the current goes through the resistor. It doesn't even see the RO. So in order to get the advantages of cascoding or gain boosting, you need to have the same R looking down as you do looking up. So if you do gain boosting down here, you also have to do gain boosting up here. So if I wanted to gain boost this, I'd have 1, 2, 3, 4 amplifiers. If I wanted to gain boost this, I would have 2 amplifiers here. Okay, I'd love to ask if there's any questions, but it's hard to do. Okay, so we've gone from passive load to active load. We've cascoded, and now we've gain boosted. Okay. And those are the main 4. You'll see various pictures that look kind of confusing, that looks really hard to figure out what's going on. But if there's an amplifier, if it's cascoded, so you see 2 transistors stacked here, 2 transistors stacked here, 2, 2, and then there's an amplifier to the second transistor, then hey, that's probably gain boosting. Okay. Another way to increase your gain, and that's the way we've been talking about in lab, is if you have gain stages cascaded now, not cascoded. Before it was cascoded. This is cascading. If you have one amplifier that takes, so we've got A1 here, its output goes to A2, and the output of A2 goes to A3, then you just multiply the gains to get your final gain. Let's see what else we have here. Okay, so let me just talk about, let's go to, okay, so we won't talk about the biasing necessarily, but this right here, if you look at this, you've got your inputs going to these transistors, then you have another transistor on top of it, and then you have V out, and then you have PMOS up above. So that is cascoded. I don't see any amplifiers, so I know it's not gain boosted. Then I have this tail current source down here to make it to make the differential pair type thing work. So this is a telescopic op-amp. There's another way to build telescopic op-amps. Okay. And that's called a folded cascoded op-amp. Okay. So the problem with a telescopic op-amp is that you have 4 transistors and then you have a tail current source. So that's 5 transistors stacked. The folded cascode lets you build an op-amp with only 4 transistors stacked. So that lets you drop VDD just 1 transistor's worth of basically a VC sat. So you can have a VC sat more V out swing. Or if you have a really low supply, that that might make it so you can build an amplifier, whereas if you had to have it telescopic, then maybe you couldn't. Okay. So this circuit right here uses the same mechanism as cascoded, a differential cascoded op amp. In other words, a telescopic op amp. Let's see how we want to do this. We've got biasing circuitry over here. So here's our DC. Here's the biasing circuitry that generates voltages. So that's generating a voltage. That's generating a voltage. This is all DC. Okay, and that voltage is going to M9 and M10. So these are current sources. They have a constant current going through them. Okay, and a fixed current. Okay, over here, I don't have these sizes. Do I have sizes on them? I don't. Okay, do I have a better picture? Let me just see something real quick. Okay, assume that, well, that's okay. All right, so let's not worry about the size of those right now. Just know that these have IREF going through them. So here's IREF going through the biasing circuitry, generates a VGS, which for those who are not used to working with MOSFETs, that's the same as VBE. So this sets the VBEs across here, which is going to put IREF through both of these branches. Okay, those are fixed currents. Okay, let's see what's going on over here. Let's set V1 equal to V2. We've got a transistor over here. Let's look like it's being biased off the same biasing circuitry over here. So this set a VGS over here to conduct IREF through these two. Here's another one. This one also has IREF through it. It's actually biasing M13, so it also has IREF going through it. Okay, if you have IREF going through M13, and let's say you set V1 and V2 to equal voltages. Okay, you have IREF going through here. If you set these to equal voltages, now equal current has to go through both sides. If you have IREF going through M13, that means you have to have IREF over 2 going through both sides here. These are coming down. This is putting IREF over 2 down into M10, and this is putting IREF over 2 down into M9. Okay, so if these two branches are supplying IREF over 2, and these are conducting IREF, that means these two branches right here also have to be conducting IREF over 2. And in that way, if IREF over 2 is coming down here, and you have IREF over 2 coming in here, they sum and give you IREF, which is what this is telling this one to conduct. Okay, so you have IREF over 2 coming through both of these sides. You have IREF over 2 coming through there. They sum to make IREF. Okay, let's do a little experiment here. Let's raise V2 a little bit. And this is tricky. If we were in class, I'd be saying, okay, if I raise V2, what happens to the current through M2? And since you're so used to using NMOS and NPN, you'd say, oh yeah, you raise it, it increases current. But remember, this is a PMOS here. So if you raise that, you're reducing VGS, which means you're reducing current. So this current right here actually becomes IREF over 2 minus some change in I. We'll call it delta I. If this side drops by delta I, this side over here has to increase by delta I to keep IREF going through here. Okay, so if this drops by delta I, this has to increase by delta I. Same mechanism as a diff pair. Okay, let's see what happens over here. So now you have IREF minus delta I going into here, but this has to conduct IREF. So if this is going to be a little bit less than IREF over 2, now this branch has to all of a sudden conduct a little more than IREF over 2. It has to conduct IREF plus delta I. Whatever this